Welcome to the 6.5 lesson video. Today we're going to be learning about how to solve square root and other radical equations, and that is our objective for this lesson. Let's begin by talking about what a radical equation is. It's an equation that has a variable in the radicand or a variable with a rational exponent. A square root equation is an equation with a radical that has an index of 2. We've worked with square roots in the past, and you may be wondering, how do we solve a square root equation or a radical equation? First thing you want to do is isolate the radical, which means get rid of everything else before or after the radical on one side of the equation, and then you want to raise each side of the equation to the power suggested by the index. In example 1, we're asked to find the solution of a square root equation. 3 plus the square root of 2x minus 3 equals 8. The first thing I need to do is isolate the square root expression, so that means I want to do the opposite of positive 3, which is negative 3. So minus 3 from both sides. So I get the square root of 2x minus 3 equals 5. From there, I need to undo that radical. So since that's a square root, the opposite of taking the square root is squaring. And if you square the left side, you must do the exact same thing to the right side to keep it an equation. From there, I know when I square a square root, those two cancel out because they're inverse operations. So you just get the expression below the radical. So 2x minus 3 drops. That is equal to 25. From there, it's a basic two-step. So you want to add 3 to get 2x equals 28. And then divide by 2, and that means x is equal to 14. In each of these problems, you always want to check your answer, because there is a possibility of getting an extraneous solution. And just like we've done in the past, the way that you check your answer is you take your final answer and you plug it back in for the original equation. So I'm taking 14 and I'm plugging in for the x, and I want to see if that left side is equal to 8. So we have 3 in front, and then we have 2 times 14, which is 28, minus 3. That's 25 under the radical. So we're getting 3 plus 5, and that is equal to 8. So that works, and that means we got the right solution. To solve equations of the form x to the m over n power is equal to k, we want to raise each side of the equation to the reciprocal power, which is n over m. If m or n is even, then when we do this, we want to set this equal to the absolute value of x. So let's take a look at example 2, part A. We need to find the solution of the equation 3 times the quantity x plus 1 raised to the 2/3 power is equal to 12. So first thing I'd like to do is rewrite the equation and then divide by 3 to isolate the expression. Now that we have the expression isolated, I need to raise each side to the reciprocal power of the current exponent. The current exponent is 2/3, so the reciprocal of 2/3 is 3/2. So we're going to raise both sides to the 3/2 power. When I do that, I get x plus 1 to the 6 over 6, which is essentially 1 power, and that is equal to 4 to the 3/2. From there, I need to put the expression x plus 1 in absolute value symbols and set that equal to whatever 4 to the 3/2 power is, that's equal to 8. The reason why we have to use absolute value symbols is because we're working with an even root, and hopefully remember from previous sections of this chapter, when working with an even root, we want to make sure that the expression we're getting out of that root is a positive number. From there, we just need to set that equal to positive 8 and negative 8, because remember, absolute value means distance from 0 on the number line. So the two numbers that are 8 units away from 0 are positive 8 and negative 8. From there, we just need to do one step. I'm getting 7 for my first answer and negative 9 for my second answer. So those are the solutions. We do want to check our answers to make sure we're not getting any extraneous solutions. So like I said, checking each solution is necessary because when we raise both sides of an equation to a power, that may introduce extraneous solutions. When I checked both of my solutions, I found out that they satisfied the original equation, so that means the two solutions, 7 and negative 9, are valid solutions for the equation. In part B, we need to find the solution of the equation 3 times the fifth root of the quantity x plus 1 to the third plus 1 is equal to 25. The first thing I need to do is isolate the radical expression. So I want to subtract 1 from both sides, drop everything else down, and then divide by 3, because that 3 in front is being multiplied. From that point, I need to change this into exponential form. So remember, we talked about this in section 6.4, which is the previous lesson video. The index is the bottom of the fraction, and the exponent inside of the radical is the numerator, or the top of the fraction. So we have the 3/5 power equal to 8. Similarly to part A, because I'm raising this to the 3/5 power, I want to raise both sides to the reciprocal power. So the reciprocal of 3/5 is 5/3. So raise both sides to the 5/3 power. So that cancels out those exponents over there. We essentially just have 1 in the exponent. We do not need to worry about absolute value because the 5 and the 3 are both odd numbers. So once we find out that 8 to the 5/3 is equal to 32, we can drop everything else and then subtract 1, and we find out that x is equal to 31. Now let's check our answer. So for my checking process, I'm taking my final answer of 31, plugging it back in for the original. I'm deciding to change it into rational form, rational exponent form, because I think that's a little bit easier to work with. 32 to the 3/5 is equal to 8, so 3 times 8 plus 1. 3 times 8 is 24. 24 plus 1 is 25. So we find out that the solution of 31 satisfies the equation, and that means we have a valid solution. Example 3 is a real-life application problem, so let's read this together. For a meteor crater in Arizona, the formula D equals 2 times the cube root of V over 0.3 relates the diameter D of the rim in meters to the volume V in cubic meters. What is the volume of meteor crater? All values are approximate. The first thing that I notice is that the equation requires us to use meters, and the picture is giving us the diameter in kilometers or kilometers. So first thing I want to do is convert the kilometers into meters. So I know that kilo means 1,000, so I just need to multiply 1.2 times 1,000, and that's how I get my value of 1,200 meters. So I'll be using that in just a moment. Since we're solving for the volume, we need to get V by itself. And currently it's solved for the diameter. So I need to first of all multiply, or divide by 2 actually, because that was being multiplied by. So the 2's cancel out. So now we have D over 2 is equal to the cube root of V over 0.3. Because I'm taking the cube root, the opposite of taking the cube root would be cubing both sides. So that's what I'm going to do. So now the radical is canceling out. So I have D over 2 cubed is equal to V over 0.3. And the last step I need to do is multiply both sides by 0.3 because that is currently division. So I can rewrite this equation as V is equal to 0.3 times D over 2 cubed. So that's my equation solved for the volume. Now, since we know that the diameter in meters is 1,200 meters, I can use this equation and just substitute in this value for D. So I know I have 600 inside the parentheses because that's half of 1,200. And when you multiply that in your calculator, you should get a value of 64,800,000. And that would be in cubic meters. So that would be the volume of the meteor crater, and that is approximate. As I talked about earlier in the video, when we're raising each side of an equation to a power, it's possible that we would introduce extraneous solutions. So that means it's very important for us to check all of our solutions in the original equation. When we check it, if we get a true statement, that means we have a correct or a valid solution. And if we get a false statement, that means we have an extraneous solution. And hopefully this process is familiar to you from earlier on in the school year. In example 4, we need to find the solution of the equation the square root of x plus 7 minus 5 is equal to x, and then we need to check our results. The first thing I notice is that the expression on the left side is not isolated, so I want to move the 5 over by adding. So now I have the square root of x plus 7 is equal to x plus 5. I want to take care of that radical. That's a square root because no other index is identified. So we are going to square both sides. So now the radical and the 2 and the exponent cancel out. They're opposites of each other. So you get x plus 7 is equal to x plus 2 squared. Hopefully you remember from chapter 4 how to work with the sum of two perfect squares. So we need to multiply that out and we should get x squared plus 10x plus 25. And you can see that we're going to be working with a quadratic. So now I want to get everything on the right side, so I have the left side equal to 0. So I'm going to move the x over, and that means I have 9x in the middle, and now I'm going to move the 7 over. So now I have 0 equals x squared plus 9x plus 18. Fortunately, the leading coefficient is a 1, so that means we can go straight to the basic x method. 18 on top, 9 on bottom. Which numbers work? 3 and 6 work because 3 times 6 is 18 and 3 plus 6 is 9. So now let's take those numbers and write it in factored form. So we have x plus 3 times x plus 6. As you know, we just need to set those both equal to 0. So we get x is equal to negative 3 or x is equal to negative 6. Now we want to take a couple minutes to check our answers. To check negative 3, I substituted negative 3 back in for the original, and I found out that it produces a true statement, which means that x equals negative 3 is a valid solution. However, when I plugged in or substituted in negative 6 for the original equation, I got a false statement, which means that x equals negative 6 is an extraneous solution. If we're given an equation that contains two radical expressions or two terms with rational exponents, what we want to do is isolate one of the radicals or one of the terms, then eliminate it or its rational exponent. When we're given two different radicals in an equation, what you want to do is isolate the more complicated radical expression first. And then in the resulting equation, what we're going to do is simplify the expressions before we eliminate the second radical. So this will make more sense when we do example 5 together. It says, what is the solution of the square root of 2x plus 1 minus the square root of x is equal to 1? The more complicated radical is the square root of 2x plus 1, so that means I want to isolate that radical, and therefore we need to add square root of x to both sides. Just like we did in the previous problems in this lesson video, we're going to take care of that radical by squaring both sides, because that's the opposite of taking the square root. When we do that, the square root on the left side of the equation and the 2 and the exponent cancel out, so we're just left with 2x plus 1 on the left side. On the right side, we need to multiply the square root of x plus 1 by itself. So if this helps you to rewrite the expression twice, we're about to FOIL those two expressions. So the left side's still the same. And when we FOIL on the right side, square root of x times square root of x is square root of x squared, which just leaves us with x because the radicals cancel each other out. And then we get 1 square root of x plus 1 square root of x, so that's 2 square root of x. And then for the last part, we get 1. From there, I want to combine like terms. So I notice that I can take a 1x over, so subtract 1x from both sides. So I get x plus 1 is equal to 2 times the square root of x plus 1. Now I can subtract the 1's to combine like terms there. So I have x is equal to 2 times the square root of x. From there, I want to square both sides to take care of that radical. So I have x squared is equal to 4x. Now let me show you where I got that from. 2 square root of x times itself. 2 times 2 is 4, and the square root of x times the square root of x is just x. So now, it looks like I have another quadratic, so I want to move this over to the other side. So I have x squared minus 4x equals 0. We just have a binomial here, and I notice that there's a GCF of x. So like usual, we factor out the GCF, put it in front, so we're left with x minus 4 in the parentheses equals 0. If the product's equals 0, then that means one of the terms is equal to 0. So either x equals 0 or x minus 4 equals 0. Add 4 to both sides, and we get x equals 4. So those are the two potential solutions. Now, of course, we want to take a moment and plug both of those back in separately to make sure that they work for the original equation. When substituting in x equals 0 for the original, I get a true statement, so that means that is a valid solution. And the same thing happens when I plug in 4. I get another true statement, so x equals 4 is also a solution. So for the original equation that we started with in example 5, x equals 0 and x equals 4 are the two solutions. That completes our lesson 6.5. Take a moment to jot down all 6 of these lesson check problems, work through them, and let me know if you have any questions the next time we meet.